consists of vector fields on U, which is like E1, E1, E2, and E3. All of them are vector fields on U, which we can also just think of to each point we assign a vector. What we want is that such that all of these, such that for each point, the values or the vectors is E1 at x, E2 at x, E3 at x, and orthonormal basis of R3. So it's a bit of an awful lot of text, but what it actually means is that you can think of like you take your right hand, you do it again like you have like 3 vectors, and then you just move on in space and around. So we have like fill out like the whole space with these 3 vectors, and we keep track of how they change. So in 2 dimensions, what we could, for example, do is for simplicity, I take one of them to be just pointing in x direction. So that's the constant vector field. No, that's our one is also. So we just take like one vector field. So that might be a E1. And then E2 is some vector field which is orthogonal, and which is like varying also smoothly. And both of them have like length 1. And that gives you a second vector, E2. So at every point, like in the plane, you would have 2, and then of course there would be a third vector pointing in the third direction. But like essentially you can think of that you have like these 2 vectors, and you just like smoothly change them like to move along in a certain pattern. And like they are completely free. They can be varying as you want. They could be, for example, related to the like spherical coordinates or the polar coordinates, where one would be pointing outwards in the radial direction and the other one would be pointing along the angular direction, or they point like the normal x-y direction, or something else which is completely, you have like absolutely no idea essentially. So the definition is very general. You don't have any constraint except that they are like at every point these 3 vectors are related to be orthogonal and normalized. That's like the only constraint that we have. Okay, so with the frames, there was like the most important result or question was, how does the frame changes as we go to a different point on the curve? How do you compare different frames at different points and then calculate the time derivative of that? So the question is the change of the Fourier. And for that purpose, we would like to define what it is. We saw already that exterior derivative of a function measures the change of that function in all directions. So we would like to define what it means for take the exterior derivative of EI. So EI is not quite a function, right? Like EI is every vector. Maybe I do that like for the first one. Like every vector is just like to every point in U, you get three components, right? And not like a function. But like, so in order to define that, by acting with D in each component. So that means we can, like, E1 is a function from U to our Fourier. So we can write it as E1 has like three different components, say as F1, F2, and F3, where each of these F's is now just like an ordinary function. So it's like the X component of E1 is F1. And then we define that D of E1 equals D of F1, D of F2, and D of F3. So since each one of these EF1 here, EFK, is a linear map essentially from at every point. It's a linear map that eats a tangent vector and gives you a real number. It's linear. We can assemble that. That means also ER1 of dx, which is like EF1 on x, EF2 of x, EF3 of x. And that's a linear map that eats also tangent vectors as like each of these components, but then it doesn't spit out like a similar number, but like for each component we get a number. So we get a linear map that eats a tangent vector and spits out a tangent vector again. It's a linear map. And of course, there's nothing special to that we choose E1 here. So we can do the same thing as like for every other vector as well. So what we get in total that DE of EI x what you do is essentially you have a vector, you look at each of the components, there might be a changing, so there are functions of u, and what you do is you just take the exterior derivative of that function, which is like the directional derivative of the function. So you record, and then you plug all of them again as a vector. So what you get is then like a vector for each input vector v. So that was the first step, right? What we wanted to is like calculate essentially the change of the frame. So that's encoded of dE1. It's like the change of the vector E1 in the v direction. So that's that's the change. But like that was only part of the problem, right? We wanted to so there. It's like the important part here is like the change of this frame, that's dE1, but we want to do something else. We want to expand it in terms of the frame itself again. So that was the important part. So we still have to do that. Like expand these E1s, the change of E1 in E2 and E3 in terms of the frame itself. So dE1, some vector, at some point b in the direction of x. This one is a vector again. It's a vector. So because it's a vector, we can write it as a linear combination of E1. Since E1 at x, 2 at x, and 3 of x is the basis of R3, we can expand this vector in terms of ij of x. So what this means is that this one is a vector, and then there exist coefficients such that you have you calculate this vector, so you can just think of that as a vector, and this vector we can write as a linear combination of the frame again with some coefficients. And now we have to be careful because there's a lot of input going in. So this right-hand side depends on the I, the x, and the v. So this guy here also depends on x and v. And that's common because it also depends, of course, on the I, to make it like the subscript I here. So to denote the dependence on the I, we just plug that as a subscript, and the subscript is like the summation variable, which is 1, 2, 3. So maybe it's a good idea to write that out. So for example, what we have is that if you take DE1, say at some point in a certain direction, what it is like we take omega I, so the I is fixed to be 1, so it's omega 1, and then we have G to be 1, D1 x plus omega 1, 2, D2 x plus omega 1, 3 x. And similarly, you can do that, of course, for E2 and E3, and what you then change is like these ones here. They change to 2 and 3. So that's like, just like if you have a vector, you can write that as in a different way. If you have like a basis, then you get uniquely defined coefficients there. And if you remember from linear algebra, the nice thing about orthonormal bases is that they can allow you to determine these coefficients in a nice way by taking the dot product. So for example, if I want to calculate omega 1, 2, what I can do is just I take the dot product with E2. Because the dot product with E2 with E1 is 0 because they're orthogonal. Similarly, if the E1 hits like E3, we get also 0. And if E2 hits itself, then we get a norm of E2, which is 1. So, we call if we take the inner product with E2 x, we get just the coefficient. So that's the ordinary dot product. So that's also, of course, there's nothing special about choosing 1 here and 2 here, so we can do that for every element, so more general. Because E1, E2, and E3 are orthonormal, we can calculate these coefficients. Omega ij equals as EI at the point x in the direction here times ej of x. So now we got these coefficients. And because they will play like such a key role in the future, like we give them a name, and we call that they depend on x and v. What you see here from that equation, right? Like it depends on x and it depends on v. So it's also quite nice to make that dependence explicit by putting like an x and a v on the left hand side. I think the clock stopped working, so. Okay, so I give you the definition and then I think it's time to for a short break. Definition. For moving frame functions that give us vectors. Objects we now call omega I j, subscript x and b equals to d I and x and b dot product j of x are called connection forms. And the identity which was saying that d I in the direction of x equals to j omega I j and x b. Just like the identity from which they were defined is called the connection equation. So, two more remarks. So what is the meaning of these omega 1ij? So omega I j x and b measures how much the vector ei of x rotates towards the aj x direction as x is changed in y direction. So that's the geometric meaning. So what we do is, for example, we can look at which vectors do we want to compare. So say we are like here, that's our point x, and we are looking at the change to a nearby point, which would be a x of v there. So we compare, now say like the E1, so E1 and E2, so omega 1, 2, that guy measures the change of E1 in the E2 direction. E1 in E2 direction. So let's have a look. E1 was the yellow, the red one. So if you look at, you have to look at in the E2 direction with this point here. So what we do is, with this vector here, it's like this change in the E2 direction. It's very hard to draw it because I have to compare this vector here with this vector. That gives us vector here, we take it back by parallel transport. We just like imagine this vector to be now parallel to this, so we move it back, and then we change, like, look at the change of E1. So like we compare this vector with this vector, and then we get a difference. And this one is omega 1, 2. So at that point you have like two vectors, and then you go a little bit to get like two different vectors. What you do is you take like one of these vectors, you parallelly move it backwards, and compare it with the original ones that you had at that point. And then you get like a difference. And that difference is essentially measured by these omegas, the omega ij, which measures how much like these vectors rotate to each other if you move to a nearby point. So that's the geometric idea of these omega ij's. And it's not a misnomer that they are called connection forms. The whole point of like essentially why we studied differential forms is that omega ij is linear in V. So it's for every vector I get a number, so I get now a linear map from R3 into R. So omega ij is a one form. So it's really like a nice general differentiable one form for every I and j. And that's something that like it's very important. It's a bit confusing, and like essentially I don't have enough letters. The problem is that you would like to like initially maybe think that I and j refer to components of a differential form. Like if you have a differential form in R3, what we can do is like we can write that as a like has three different components. These are not the I and j. The I and j are like fixed. Like for example, they say like we want to look at the rotation of E1 in the E2 direction. So that's like given by these I and j. Yeah? And once you fix that, it's still like a differential form. So you have like a matrix of differentiable forms, and each one of them has a coefficient again. So it's like essentially you have three indices, and one of them you almost never write out. So what you do is like really just like have a matrix of the I and the j's, and for each of these numbers, from 1 to 3, you get a one form. So that's the content, and that's yeah. So you really think of that as a really huge matrix, but instead of having like numbers at each of these blocks, so like a 3x3 matrix, you have a differentiable form at that point. And I think that's enough for the first part. So let's have a 15-minute break and continue 5 minutes after 35. Okay, let's continue. So we now got these equations, these connection equations, which is saying that the change of the frame in a certain direction is given as in terms of these omegas ij expanded like with respect to the frame itself. So we would like to compare that, or I would like to compare that to the Fourier equation that we already seen. Which was that we start with t and b here, and we take the time derivative, and what we end up with is that then there's always the question of the signs. We double check. And these equations are very similar, that they also say like the change of the frame, that is the left-hand side, equals to something that involves the matrix, that's these omega ij times the original vectors again. But like this matrix here has certain properties. The first one is that this one is always minus on the other side, that that's skew symmetric. Right, like if you have tau here, then here on the opposite you have minus tau, and similar with kappa and minus kappa. So that's the first question. Does this always hold for our omega isj's? And then there's the second difference, but like that one I will discuss in a second. So let's have a look if we can prove that omega ij skew symmetric. Who remembers like the proof of these equations and remembers why kappa was here and then minus kappa there? What was the reason for the skew symmetry of this matrix? Yes. So the reason was essentially that we had the orthonormality, which says which we could exploit. So similar here, we have. That's why we would also expect there is some kind of relationship. And similar here, we have EI to be like an orthonormal basis. So what we can do is we can use our original trick. We say that E1 and EJ, the inner product, say at like a different point. This one is always a constant function. It's 0 or 1. 1 if I and j are the same, and 0 if they're not the same, because E1, like EIX is like an orthonormal basis. So this one is either 0 or 1, but in other cases it's always constant. It doesn't depend on x. So now we do our favorite trick. If you have like a constant function, we take the derivative with respect to what it might depend on. So like, with respect to x. Take directional or actually exterior differential. So what we do is we get 0 because it's a constant function, and then we take dI times ej. So now we use that, like d is a linear operator, so we can just, or like the Leibniz property essentially. So this one is dE. Maybe I take like x and b as well. So what we have is a dE I in x direction and v times ij plus ei of x times dE j. X and b. So that's the Leibniz property. And now we look at the definition. This one here is really nothing else than omega ij at the point x in the v direction. So that's the definition that it's over here. That's the definition of the connection forms. And now we use the same equation, but like with the opposite here. So like it doesn't matter on which side I take the inner product, it's symmetric. But then if I look, here we have the dEi with an I here, but here we have it with the j. So this is then the omega I x and b. So we get 0 equals omega ij and plus omega ji. So this follows that omega ji equals to omega ij with a minus sign. So skew symmetric. So it's skew symmetric in I and j. So we can think of, can write, like if you think of that as a matrix, omega ij, it has like essentially only three elements that are left. It's omega 1, 2, omega 1, 3, and omega free, and then 0 on the diagonal because of the skew symmetric, and then the off-diagonal ones here are automatically determined by the skew symmetry. So in particular, only omega 2 free are independent values. So you don't have to calculate, if I ask you, for example, to calculate the connection forms, you don't really have to start again like with omega II where the diagonal. You already know that they are like have to be 0. So you only have to calculate these 3 elements in order to calculate the whole connection form. And that's very similar to, as I motivated, similar to the skew symmetricity over there. So what is the difference between like these connection forms and the skew symmetric matrix over there? Like there's 2 differences. So what are the 2 differences between this skew symmetric matrix and this matrix of connection forms? Like one is like very obvious, right? Like here we have like always a 0, while here that element might be non-zero. So that's like the first thing that you notice. And the second one is that these ones are